Wow, this problem is pretty tough here.
Hey, you need some help, man?
Yeah, man.
What class are you in?
Dynamics.
Oh, me and my buddy here are
Yeah.
seniors. We're mechanical engineers. We can help you out.
Alright guys, here's the problem. We have 3 gears fixed to a rod. Here's the dimensions from A to C. The center is 8 inches. The radiuses of each gear is 2 inches. Here's the given weights. And we need to find the moment put at B in order to achieve this. Angular velocity of the rod at 2.5 seconds. So my professor gave me this diagram, but I was kind of confused on how it moved and stuff.
So you said gear B was fixed, right?
Yes.
So these gears A and C are actually spinning, they're rotating, and they're translating around gear B.
All right, man. So the first thing you're going to want to do is analyze the linear and the angular velocity. First, we need to convert the angular velocity into radians per second. So we have revolutions per minute using dimensional analysis to get 8 pi radians per second.
All right.
We also know that the velocity of A is equal to the velocity of C because of symmetry about B. And that's going to equal 2r omega. We also know omega A and omega C are equal because of symmetry as well. And that's equal to VC over R. But VC was already found above as 2r omega.
Alright, so I got to this part. Impulse momentum at gear C. So at first there is no momentum, and then there's an impulse. But I'm not sure what to do with the center.
Well, you are right that there is no initial angular momentum because the problem says it starts from rest, so nothing's spinning, nothing's moving. But right here, the angular impulse at C, you are missing the linear component right here. It's the linear momentum, and we're going to multiply that by time just to get rid of the integration. Because
So the next thing you're going to want to do is sum moments about the point D. We're not very interested with the force here, so we want to sum moments about D to get rid of that force. We know that that's equal to impulse, which is always going to equal the mass times the velocity times the radius plus the moment of inertia times the angular velocity. But that's going to be equated to the external forces we see on the diagram, which is going to be the linear momentum times time multiplied by the perpendicular distance, which is r. So we see that mcvcr plus ic omega c is equal to LTR. The next thing you're going to want to do is sub in the fact that omega c is equal to 2r omega of the rod, like we had said previously.
Alright.
The next thing we're going to want to do is substitute in an equation that we have for moment of inertia. We know the moment of inertia of a plate is 1/2 mr squared, so that's where we use 1/2 mass times c multiplied by the radius squared. And then we're going to carry over the 2 omega of the rod, because earlier we had said 2 omega of the rod equals omega of the gear.
So I think I'm starting to get it now. So now we're going to do the impulse momentum at the rod. At first, there is no momentum. And then here's the forces. LT, which we found before. The forces at the pin, BX and BY. And then the moment that we are going to be applying. Here's the final, this I think is the final moment, angular momentum. So now I'm taking the moments about point B. We have the moment that we're trying to find, and then the two forces, LT.
So the final step in your solution process is going to be a substitution.
Alright.
We're going to use the fact that this equation has an LT in it. We'll call that star. We have this second equation over here, also involving LT. We'll call that double star.
That makes it easy.
What we want to do is substitute star into double star. So there's one more thing you need to be careful with before we finish the problem, and that's units. So the radius is given in inches, but if our moment is in foot-pounds, we need to convert inches to feet by dividing by 12. We also need to convert our weight given over there into a mass, because we're actually not given mass.
All
We're
right.
given weight in pounds. We need to divide by 32.2 feet per second squared, which is the English acceleration due to gravity. Do you agree?
Yeah, you have to do that.
And then from there, everything else is trivial, and you get 0.306 foot-pounds. Hey man, how's class been?
Oh, what's up, guys? Good. Just got my exam back.
What'd you get?
82.5, baby.
Great job, buddy.
Thank you, thank you.